Homework 15. First part of this homework is all about how to do a titration, these first 3 questions. So you obviously need to complete it, each one individually. I'll briefly, in this space here, draw a diagram of the apparatus and talk you through how to do a titration. There is a video in the separate science area that you can watch. You can actually watch me doing a titration. It's tremendously exciting, if it helps, but I can talk you through it here. First thing you need is a burette. A burette is a long, thin tube. And it's got a tap at the bottom of it, that circle with a cross through it. And it's very thin, which means even a small difference in the volume of liquid makes quite a difference in height, so we can read it off, and there's measurements the whole way down it, so we can make accurate readings, down to really 0.05 of a centimetre cubed. So 0.5 a centimetre cubed, I should say. So we can measure liquids quite accurately with these things. So that's a burette. It's got 1 R and 2 T's. Now, ordinarily, if we're doing acid-alkali titration, we'd normally fill that with acid. Okay, so we can say the acid can go in there. So down the bottom here, we're going to have ourselves a conical flask. Conical flasks are probably better than a beaker because they've got a narrow top. So if there's any splashes, they're less likely to come out of the top. And so we'll draw ourselves a conical flask down there. Now, we will put that on a white tile. Now, often when we're doing these explanations, people forget the white tile because it seems a little bit less important. But it is quite important because when we get to neutralisation point, how do we know it's neutral? We have an indicator in the flask, and that's a colour change. And so if we have this on a white tile, then it's very easy to see the contrast change, the change in colour. If it's on a grey retort stand or a black retort stand, then it's less easy to see the colour change. So the white tile is quite important. Now, so we have the acid in the burette, we're going to have the alkali in the beaker. Now we need to have a set amount of alkali to neutralise. Okay, so the alkali is going to be in here. So it's often we'll choose to use 25 centimetre cubed of alkali. So how do we measure that out? We measure that out with an even thinner glass tube. Okay, and that even thinner glass tube is called a pipette. Okay, so it's tremendously thin. At the top of it, it has a mark, so we can see where 25 centimetre cubed is, and it's so thin that the tiniest difference in volume of liquid inside the pipette makes a big difference to the height of the liquid, so they're very, very accurate. So this is called a pipette, and it's got a big glass bulb in the middle, so we can actually get 25 centimetre cubed in, but it's just thin around the marking point. So this is called a pipette, and we're going to fill that with alkali. So we'll just have a little beaker of alkali here that we can suck our alkali up from. We have a pipette filler on the top, which is just a big squeezy rubber ball which provides the vacuum to suck up the liquid. So there is our alkali. So once we have our 25 centimetre cubes, this is going to be 25 centimetre cubed of alkali, we take it from there and we put it into the conical flask. And we add acid and titrate the acid against it until we have that neutralisation point. Now, if we're doing an acid-alkali titration, we need a good indicator. Phenolphthalein is often the one we use because there's a really clear colour change. It's like a switch. Okay, it is pink in alkali and colourless in acid, and you do need to remember that colour change. So you should be able to list the equipment. You should be able to say how we're going to measure out the alkali, and you should now be able to write a detailed method. We stop adding the acid the second it goes neutral, of course, and record it off. Repeat it a couple of times, just check the results the same, average the final result, and then you've got exactly how we can do that. Next one, calculations, just calculation revision now. Magnesium carbonate by mass contains 22.22% magnesium, 11 carbon and 44 oxygen. What's the empirical formula? So empirical formula. So we've got 3 elements here, so we need to divide the page into 3. Okay, and we need to write each element at the top of each one. So magnesium, carbon and oxygen, and we need to write moles equals mass over atomic mass for each of them, because we need to do this calculation 3 times. Oops, moles equals mass over atomic mass, and moles equals mass over atomic. And do write it out 3 times. It just shows the reader you know what you're on about. Every time you write it out, it goes into your head a bit more. Now, I know we haven't got grams, which would be usual for mass, but we have percentage. Now, we're only looking at the ratio of magnesium to carbon to oxygen, so percentage is our mass. So we're going to put 22.22 divided by 24 in there. Okay, it's going to be answer. That's going to be just less than 1, and so that will be our amount of magnesium at the end. It's going to be just less than 1, about 0.95. Just looking at that, you need to do it exactly. I've just guessed that. Looking at the numbers in my head. Okay, so once you've done that for magnesium, you can do it for carbon as well. So carbon's 11.11 divided by the atomic mass of carbon, 12. You're going to get a number for carbon, you're going to get a number for oxygen. Let's just call that X and that Y. Okay, you need to look at the relationship between these numbers. Okay, whichever is bigger is going to have the bigger number in the formula, and you need to make sure you've got the smallest possible whole number in that formula. For example, let's just say this was Mg, let's just say this isn't the answer, Mg 0.95, carbon 1.9. Looking at those two numbers, now this isn't the answer, but just looking at those two numbers, that number there, the carbon 1.9, is bigger than the magnesium. Okay, so in the formula, okay, Mg is going to be smaller and carbon would be bigger if these were the numbers. Okay, next question, how much bigger is that number? Okay, we're just looking at it, I can see exactly how much bigger it is, but let's just say you can't see how much bigger it is. Take the big number and divide it by the little number. Okay, now if you do that, its answer's 2. Okay, 1.9 is the big number, divide it by the little number, 0.95, the answer is 2. That tells us, okay, the formula would be MgC2. Okay, anyway, as I said, those are not the answers. Okay, you need to work out the answers and then work out the relationship between them, and the formula would be MgCO, whatever those numbers are in that relationship. Next calculation. How many atoms are present in 3 moles of carbon dioxide? Okay, so it's number of molecules. Number of molecules equals the number of moles times the Avogadro constant. Okay, so moles here is 3, Avogadro constant is 6.02 times 10 to the 23. Remember, the challenge there is putting that number into a calculator. Just do that now. Here's our calculator. Okay, so we're going to do 3 times, that's a multiply, 6.02, 6.02. That's not multiply there, okay? That's the mistake lots of people make. It's times 10 to the x, that button there. Times 10 to the x, 23, equals. So that's going to be 1.806 times 10 to the 24, okay? That's the number of molecules, okay? This question asks how many atoms are present in 3 moles of carbon dioxide. So we've got the number of molecules in 3 moles of carbon dioxide, but not the number of atoms. So carbon dioxide, okay, CO2, okay, contains 1 carbon and 2 oxygens. So you're going to need to multiply that number by 3, because there's 1 carbon and 2 oxygens, 1 and 2 is 3, and that will give you the final answer. Have a go with that. Next question, calculating quantities. What mass of carbon dioxide is made when 26.5 grams of sodium carbonate is neutralised by excess nitric acid? First thing we do, add this information to the equation. What mass of carbon dioxide? That's the question mark. There's our carbon dioxide. Okay, that's what we're trying to find out. Is made when 26.5 grams of sodium carbonate. So you've got to find sodium carbonate down here now. That's that one. So we're going to write 26.5 above it. Okay, so we can cross out everything else that's of no interest to us. Now, I've done quite a few of these recently. I've used different examples. In case you're still struggling, I'm going to use this example this time. I'm not going to do it all for you, but I'll help you with it, okay? So calculating quantities have 3 stages. First one, moles. Moles equals mass divided by formula mass, okay? So we need to calculate the formula mass of whatever you wrote the mass above in this stage. We wrote the mass above sodium carbonate. So the formula mass is going to be of sodium carbonate. So sodium carbonate's got Na2, so it's Na plus carbon plus 3 oxygens. So the first thing you need to do is work that out, okay? Sodium's got atomic mass of 23. Carbon's got an atomic mass of 12. And oxygen's got an atomic mass of 16. So that's going to equal a number, okay? And that number is going to go down there. The mass is 26.5. We wrote that above it. So 26.5 divided by that number, that's going to give us a number of moles. Stage 2, stoichiometry. So we write out the bit of the equation that we need. We need this bit and this bit. That is going to be Na2CO3 makes CO2. Okay, so we're looking out the big numbers before these substances. Now, we haven't written any big numbers down. There was a big number before the nitric acid, a 2, okay, but we're not interested in nitric acid. There's no big number there, there's no big number there, so in that case, the big number is 1. So the next question we have to ask ourselves is that number the same, or is one of those numbers bigger? Answer, it's the same. 1 and 1 is the same. What that means is whatever number is there, okay, is going to come down here now, okay, and that number will be the same for the number of moles of carbon dioxide that is made, and we don't need to do anything to it. So that number of moles is the number of moles of sodium carbonate. 1 mole of sodium carbonate makes 1 mole of carbon dioxide. If that number happens to be, I don't know, 0.5 moles of sodium carbonate, it's not. It would then make 0.5 moles of carbon dioxide. If it happens to be 48 million moles of sodium carbonate, it's not. It would be 48 million moles of carbon dioxide. Because these numbers are the same, whatever that number is there, it's going to be that many moles of carbon dioxide. Final stage, moles again. These always go moles, stoichiometry, moles. But we need to rearrange this moles equation to make mass a subject. So mass equals moles times formula mass. This time it's the formula mass of the question mark. Okay, so we have to calculate a new formula mass. That's carbon plus oxygen plus oxygen. Well, there are our numbers there. Atomic masses, so you can put those in and come up with the formula mass of carbon dioxide. You need to multiply that number, okay, by the moles that you brought forward from here. Okay, and whatever that is, that multiplied by the formula mass of carbon dioxide will be our final answer, and it's going to be in grams. Good luck with that one. Last question. Look at the solubility rules. These need learning, and state whether these are soluble or insoluble. You may be thinking, solubility rules? What on earth are those? Well, the latest version of the book that I've put together, they're on page 121 now. Depending on when you're watching this video and what version of the book, that might change slightly. So let's just show you what they look like again. Here are the solubility rules, okay? So we have dissolves in water soluble in this side of the column, and doesn't dissolve, it's insoluble in this side of the column. So let's just say, you know, we're looking at copper nitrate. So we need to go around here and find copper nitrate. It says all nitrates are soluble and there are no exceptions. There's nothing insoluble, so copper nitrate's soluble. Let's say we're looking at potassium carbonate. Okay, well, carbonates are down here, and it says doesn't dissolve insoluble. So potassium carbonate, you think to yourself, insoluble. But you just need to check the other column to look for exceptions, except those of sodium, potassium, and ammonium. So potassium carbonate is soluble, okay? So these solubility rules, I'm afraid you just have to learn them, because you do get questions like this, okay, in the exam. And they're often multiple choice. They'll put 4 compounds down, they say which of these is insoluble or which of these is soluble, and it's a 1 in 4 guess if you haven't learned them. If you've learned them, it's the easiest mark in the history of chemistry, but the reality is most people get it wrong. Okay, so have a go. Look at those on the solubility tables, and hopefully you can get some marks there. Okay.